Evolucija našeg svijeta uvelike ovisi o tehnološkim resursima, stručnom znanju i granicama sposobnosti. Današnji stupanj dosjetljivosti i inovativnosti znatno ubrzava taj proces. Bili smo na površini Mjeseca, lansirali satelite da kruže oko našeg planeta i motre što se događa tisućama, ako ne i milijunima kilometara daleko. Razvili smo svemirske letjelice, robote koji prkose gravitaciji i uređaje koji nam omogućuju da dišemo kad nema zraka. Čini se da nema tog izazova koji ne možemo svladati ako se potrudimo. Jeste li se ikad zapitali tko projektira i gradi te nevjerojatne izume? NASA je svakako jedan od globalnih predvodnika u inovaciji i unapređivanju evolucije čovječanstva. Kako to radi?
3, 2, 1, 0. Ignition. Liftoff of the Falcon 9 and Crew Dragon. Go NASA. Go SpaceX. Godspeed. Spot a dog.
– 1958. predsjednik Eisenhower potpisao je zakon o osnivanju NASA, državne agencije za zrakoplovna i svemirska istraživanja u kojoj će proučavati, razvijati i primjenjivati postignuća svemirske znanosti. Među njihovim najpoznatijim pothvatima ističe se svemirski program Apollo, koji je obuhvaćao niz misija na Mjesec, svemirska postaja Skylab i revolucionarni raketoplan Space Shuttle. NASA surađuje i u projektu Međunarodne svemirske postaje. Njezin znanstveni rad usmjeren je na proučavanje našeg planeta, širenje spoznaja o fizici Sunca, istraživanje sunčeva sustava, planiranje svemirskih misija i analizu različitih svemirskih pojava. Talentirani i odlučni NASA-ini znanstvenici i inženjeri pomažu cijelom čovječanstvu u napretku i razvoju tehnoloških sposobnosti. S 18 centara raspoređenih na 18 lokacija u SAD-u, NASA je danas posebno poznata po inovativnoj tehnologiji namijenjenoj istraživanju svemira. Ističe se i u pionirskim projektima suradnje na području inovacije. Posjetili smo istraživački centar Ames u Mountain View u Kaliforniji kako bismo saznali više o NASA-inim inovacijama i ljudima koji su zaslužni za njih. Centar je smješten u blizini novog sjedišta tvrtke Apple i korporacijskog kompleksa Googleplex. NASA-ini znanstvenici po prirodi su inovatori. Zadatak im je osmisliti tehnologiju koja još ne postoji. Istraživački centar Ames u sjevernoj Kaliforniji obuhvaća različite pogone za istraživanje i razvoj, laboratorije i poligone za testiranje.
I'm a robotics engineer working on our rover to get science outside of our atmosphere and enable planetary exploration. So robotics is a broad field. We have a lot of computer scientists, electrical engineers, mechanical engineers, and on my side, I'm more on the mechanical part. So I've been working in building and integrating most of the instruments during the project. And then I'm also working as a systems engineer, so basically getting everything to work together and communicate together. We cannot directly send astronauts easily to the moon or Mars, but robots are much more suited to those tasks. And so what we hope is that those can be our eyes and hands on the moon or Mars again, so that we can do the same as we would do here in a lab, take samples, analyze it, and then give back some scientific results.
Roboti, umjetna inteligencija i autonomni uređaji iznimno su važni komplementarni elementi NASA-inih inovacija.
Right now, our focus is on the moon, as is NASA's national focus, is on a return to the moon. So our goal in returning to the moon is to land in a polar region. So we've landed at the equatorial regions on the moon, but we've never explored the poles. And a goal in exploring a polar region of the moon is to search for resources that we could use to build a lunar base, to live off the land, so to speak. So water is a key resource, and to that end, we want to land at one of the lunar poles and map the water. And to do that, we need to get sensors to the surface and then be able to have mobility for those sensors. So we're building a robot with mobility to be able to explore the poles and search for the water, see where the water is. Not only where it is on the surface, but where it is underneath the surface. And when you get to a point, you're going to stop and you're going to look around and say, where am I? And that rover is going to send you pictures back automatically. Now, if you say, wow, I like what I'm seeing here, but I need more, you have the option to take more pictures. But every time you do that, you take up time. And if you think about driving with these rapid-fire command cycles, if every command cycle you need more pictures and you need more data, what you can do over the course of your mission is going to be greatly reduced. And that's one of the reasons we run these simulations, is to understand our productivity. On the moon, right, we don't really have weather in the conventional sense, right? We have weather, space weather from the solar wind. But it's not like Mars where you have wind and clouds and conventional weather that we can relate to. The difference is the lack of atmosphere creates different lighting conditions. And then the temperature, as I mentioned earlier. And then, of course, we have at the poles, the angle of the Earth is very low over the horizon. So that creates issues in communications. And our vehicle is going to be solar powered, charged by the sun. And the lighting at the lunar poles is changing very quickly. And so we have to make sure that the batteries stay charged so that we can operate, right? Whereas the older Mars rovers were solar powered, but the current Mars rover, MSL, the Mars Science Lab, that's nuclear powered. So they don't have to be concerned about lighting in that way.
Većina NASA-inih znanstvenika visoko su kvalificirani inženjeri i fizičari koji primjenjuju niz tehnika i teorija kako bi osmislili inovativna rješenja za probleme s kojima se susreću pri istraživanju svemira.
My personal background is in robotics, and during my graduate school career, I worked with planetary rovers in the Atacama Desert of Chile. And we were trying to learn what's the best way to use a rover to look for life in extreme environments, possibly on other planets. I was obsessed with space as a child, and my daughter is too. There are 3 Astrobees that will eventually be on the International Space Station. They're next-generation free flyers that will be used by guest scientists to test out their ideas about free-flying robotics in space. It takes off from its own charging station, and it can fly around, and then it can autonomously return with no astronaut support. There are 3 main functions for the Astrobee. First is the guest science I was talking about. Second, they'll be used to look at getting situation awareness for crew activities. So the state of the art today is the crew themselves, the astronauts, have to set up a camcorder to take a video of their own activities. But with the Astrobee robots that have their own cameras, ground operators will be able to reposition the camera to get a better view of what the crew are doing. A third main function is to take sensor surveys throughout the International Space Station, looking at things like how loud is the sound, what are the CO2 levels, what are the radiation levels. Those are things that the crew can do today, but they're very time-consuming, repetitive activities, and we want to free up their time by using the robot to do that. These robots are in many ways a lot like a multi-copter drone that you might have at home. However, they're working in the zero-gravity environment of the International Space Station. One of the things that's important to us is to be able to have the robot move instantaneously thrust in any direction and turn about any axis. It can pretend to be any kind of a satellite based on what the guest scientists want to use it for. Another challenge about working in the International Space Station is, you may not know this, but it has glass windows with space on the other side. So it's very important for us not to break a window. You may know that NASA is developing a new space station called the Gateway that will operate near the Earth's moon. One of the things that's very important about the Gateway is that, at least to begin with, it will only have astronauts aboard for about 6 weeks out of the year. During the rest of that time, it will have a big issue just taking care of the space station. And so intravehicular robots like Astrobi and like the Robonaut that we've been testing on the International Space Station are going to be an important part of how do we do that caretaking function on the new space station. This is the certification unit for Astrobi's robotic arm. The arm slides into the top aft bay here, and this is the stowed position for the arm, but then we stow it inside the volume of the Astrobi so that Astrobi stays compact and it can move through tight spaces. But then when we want to use the arm, it will fold out and deploy like so. And then it has 2 degrees of freedom, these 2 degrees of freedom. So what we can do with it is we can grasp a handrail, and then when Astrobi is grasped onto the handrail, we can maneuver the body of Astrobi using these 2 axes here. So basically we can point the cameras on the front of Astrobi in any direction that we like. And that's important because when we're taking video of astronaut activities, we don't want to unnecessarily intrude on their space or create a lot of noise around them. So we grasp onto a handrail, we turn down the propulsion, and that gives us a nice quiet environment to observe them in.
I would say in regards to autonomy, right? And autonomy is a word we use quite a bit to mean different things. So when you're controlling any vehicle in space, the command latency, and what I mean by that is from the time you send a command to tell it what to do to the time you find out what happened, right? So say you're doing Internet of Things or driving a radio-controlled car or operating a drone. You've got what we would call real-time command and control, meaning this, from the time you send the signal to the time you see the result is pretty much instant. So that's what we would call real-time.
Razvoj uređaja kojima se može upravljati s udaljenosti od mnogo tisuća kilometara zahtijeva veliko iskustvo te iznimnu sposobnost predviđanja i planiranja.
So if you're on Mars, depending on where Mars is in its orbit, that could be up to 40 minutes. You think about that. I'm going to send a command, and 40 minutes later, I find out what happened. So that's a very different way of driving a vehicle. And to do that, you have to build sequences of commands, validate those, and then send up a sequence that executes over a long period of time, sometimes even multiple days, and that's what our colleagues at the Jet Propulsion Laboratory do to operate a Mars rover. For us, we'll be on the moon. Our round-trip latency, the time from when we send something to when we see what came back, is 6 to 10 seconds normally, but it can range as high as 25 seconds. And if you're thinking, wow, light speed round trip between here and the moon is around the order of 3 seconds roughly, okay? But there's overhead with the communication system that creates that uncertainty. So we have to plan for command latency on the order of seconds, not minutes.
So this is our K-Rex rover. It's a research and development platform that we have been working on for about 5 years now. And we have been developing a lot of different algorithms and supporting a lot of different projects. So a lot of the work was focused on navigation and mapping to start with, to get the rover basically to know about its surrounding and get a grasp on its environment in order to characterize what is drivable terrain and non-drivable terrain, and then get information back for the scientists to work with. And then afterwards, a lot of the work we have been doing is supporting science instrument maturation, where we take instruments that we place on that rover so that we can test them in remote places on Earth just before they would be sent on a mission to the moon or Mars.
As a government agency, we're very open at NASA, and we work with our industrial partners, and part of our charter is actually to make our data available to industry as much as possible. So we have a process for open sourcing, for making our software open source. I think open source used to be somewhat of an outlier here, and it's growing tremendously in popularity. And in addition, a lot of what we do now, things that we used to do in-house, including building spacecraft, And when I say in-house, I don't mean they weren't contracted out, right? But we have public-private partnerships now, and an increasing amount of our work is done that way. So you may have heard of the Commercial Crew Program, right? SpaceX and Boeing will be delivering crew to the space station. In our lunar exploration plans, public-private partnerships are a cornerstone of how we're going to do that. Yeah, so in the past, I think the competition would have been who's going to win the contract to build the big vehicle. And there are still competitions in those public-private partnerships to see who's going to get various aspects of those things. But for the technology that we develop in-house, where we can, we make it available so that our partners can use it. If you look at Open Mission Control Technologies, it's on GitHub, and we have an informational website. You'll see we have a huge number of users, a really diverse number of users of spacecraft, different types of spacecraft, more than you'd get if we were not open source. So we're really excited about that.
NASA je svjesna da je istraživanje svemira beskonačna pustolovina. Umjesto da njezini stručnjaci sami pokušavaju prevladati izazove s kojima se suočavaju, surađuju s brojnim tvrtkama iz privatnog i javnog sektora. Tu je i golem broj registriranih patenata i nacrta izuma koji nikad ne dođu u fazu proizvodnje. Jednostavno, nema dovoljno kapaciteta da bi se svi mogli razviti i testirati. Zato je NASA pokrenula 2 programa suradnje s malim tvrtkama. To su program zajedničkog istraživanja i usluge prijenosa tehnologije, koji omogućuju skladnu suradnju s malim tvrtkama diljem Sjedinjenih Država. Programi su usmjereni na tvrtke s manje od 500 zaposlenih, koje prvi put imaju pristup takvim resursima i mogućnostima. Zainteresirane tvrtke mogu se uključiti u istraživanje i razvoj na saveznoj razini uz potporu i blagoslov NASA. Time znatno proširuju granice svojih tehnoloških mogućnosti. Dodatni je poticaj profit koji mogu ostvariti komercijalizacijom NASA-ine tehnologije. Mnogi poduzetnici i inovatori ne znaju da NASA ima i mrežnu bazu podataka s javno dostupnim popisom svih neiskorištenih patenata. Svatko može zatražiti licenciju za razvoj i komercijalizaciju. Pristojbe za izdavanje licencije iznose između 5 i 10 tisuća dolara, što znači da su doista mnogima dostupne. Osim što je spremna ustupiti svoje revolucionarne nacrte, patente i licencije, NASA pod određenim uvjetima može i financirati projekt, te poticati i pratiti razvoj tehnologije sve do faze komercijalizacije i prodora na tržište. Ljudi su od pamtivijeka očarani svemirom i tajnama koje se skrivaju onkraj našeg planeta. Naša potreba za istraživanjem i inovacijom dovela nas je dalje nego što smo ikad mogli pomisliti.
So there's a lot of uncertainty in exploring a polar region, right? So we've been to the equator, we've been to Mars, we've done a number of solar system explorations, but the conditions at a lunar pole are quite a bit different than what we would find on Mars. So, for example, temperature. The temperature on Mars, it's pretty cold, but it even gets above 0 degrees. At the lunar poles, we're talking 40 degrees above absolute zero in a permanently shadowed region, okay? And there are regions of shadow on the moon that haven't had light in hundreds of millions or even a billion years, okay? So very different conditions on the moon. No atmosphere on the moon, whereas we got a thin atmosphere on Mars. So to deal with that uncertainty, to understand what sort of a robot we need to design, we run a series of simulations in this lab. And to do that, we combine different types of software. So we have software to plan traverses, okay? Given the set of constraints we have and how we have to operate, how far can we drive in a given amount of time? When are we in sunlight? When are we in shadow? What's the temperature? So we simulate that. And then we have that simulator creates that environment that we expect to find. And then we have a rover driving tool so our drivers can do test runs. And then from there, we use the mission control software I was talking about to display the data.
Nekoć smo tehnologiju zamišljali kao računalnu opremu, ali programska podrška i prednje sučelje s vremenom su postali temelj inteligentnih, brzih i naprednih kontrolnih sustava.
So I'm going to show you how to build a display layout that flight controllers can use. In the past, flight controllers took months and months to build this because I had to go back to programmers and then they had to build the displays. But now they can do it in real time on their own web browsers. I'll show you a little bit of how this works. You have composable objects that you'll create. The one we're creating right now is called display layout. It starts off with a blank canvas like this. We have objects that we have created in the past before, so we can reuse it right now. So we'll drag and drop the rover image right here. Let's say I want it on the left end of the display instead of the right this time. And then we have a couple of pots that we can take in. So just drag and drop. Super intuitive, super easy. These tools give you the ability to create any kind of customizable tools for your display layout. A couple of summary widgets. These are kind of like car idiot lights that tell you if there's something wrong. So here you have a fully customized control center. And it just took me less than a minute and a half to put together.
We build software so that mission controllers who operate spacecraft can see their data and use their data and command and control our spacecraft, mostly robotic spacecraft. So what we've done is created a technology that allows a mission controller to think about their data without having to consciously think about what software application. And we've put all these different things under one roof. And by doing that, we've created a level of integration that allows us to do things we couldn't do before. So think about, I've got all my data in one place now, okay? I'm not going to all these different pieces of software, and I'm not thinking, well, what piece of software do I need to do this thing? And I can build these visualizations of what I need to look at. Can all be put together without writing a line of code, okay? A mission controller can get a canvas and just by drag and drop can build every display. So we think that makes life a lot easier for people.
Inovativni razvoj specijaliziranih uređaja s daljinskim upravljanjem presudan je za sigurno putovanje opasnim područjima galaktike.
All right, welcome to the microgravity test facility. This is where we test moving Astrobe around in a full 6 degree of freedom motion to simulate the way it can fly around inside the space station. So here's our convenient Astrobe mock-up named Buzz. Much easier to carry than a real Astrobe, which is a lot heavier. So I can show you how we would normally put one of the Astrobe prototypes in this cradle on the gantry. So we have a 3-stage gantry. It can move in X, Y, and Z. We have a 3-stage gimbal. It can move in roll, pitch, and yaw. We use this to understand how Astrobe's navigation system works. So it's able to recognize texture that's on the walls of the International Space Station and determine where it is. In the back, we've got our convenient mannequin who can pretend to be an astronaut on the ISS, and we can test whether or not Astrobe's obstacle detection will be able to pick it up.
Gradnja robota koji će raditi u bestežinskom stanju donosi mnogo izazova u fazi projektiranja, razvoja i testiranja.
Astrobe's propulsion system is a little bit different from what you would normally see on a drone. We've got these 2 propulsion modules, and each one is based around a centrifugal impeller that spins here. The air comes in here, pressurizes the plenum very slightly, and then these nozzles open in different directions to give it thrusts in different directions. Now, why did we go that way? Well, you may have seen that when astronauts are floating around inside the space station, they've got very poofy hair. We don't want it getting caught in the axle of a multirotor. So this centrifugal impeller, by only having 2 of them on the spacecraft, we can put a screen in front, and we can also keep things much quieter. That's great because there's so much hardware up on the space station that the astronauts, it's really like an occupational health issue for them. Astrobee is really a research project still at this point. It's made specifically for the International Space Station. What we're looking forward to now is developing next generation robots that will work in places like the Gateway. They'll be taking care of the station or the vehicle that the astronauts will be traveling in later, making sure that when the astronauts actually arrive, they come to a functioning facility and it's safe.
The software is called Open Mission Control Technologies, and one of the reasons we're excited about it is that it is open source. So if you look at mission control, you know, the iconic mission control from the Apollo moon landings, those have been traditionally proprietary systems for a relatively small number of people, right? Maybe for a community of a couple of hundred flight controllers, maybe a little more, maybe less. If you know, not internet scale. Think of internet scale where you've literally got hundreds of millions. Sometimes 1 billion or more users. So we made this open source because we think that the community makes the software better. The more users we have, the more eyes on this software, the better this software is. It's also a different way of building things. It is inherently collaborative. So we build this software, but by putting it out as open source, while we keep building it, someone else can take it, assume ownership, use it as their own, and then their contributions could go back into the system. So it's an exciting collaborative way for us to build software and really make that software better through use than we could ever make it with a small number of people just using it here.
So the different rover functionalities that I can show here are first the 2 cameras that we can see in the mast, which are the eyes of the robot that can be used for the robot to build a 3D map of what's in front of it, and also by the scientists to get contextual information about the place. Then we have a sensor on top, which is a LiDAR sensor. So it shoots laser beams around the place and basically tells how far every single point is. And that can help reconstruct the environment in 3D all around the robot. Then whenever we have issue with those sensors, we have an inertial measurement unit, which is located centrally to the robot that we cannot see here, that measure every single acceleration in translation and rotation, and basically helps to know what motion the robot is going through. After this, we have those antennas that are used for communication. So the robot moves to different places and always communicate back to our base station. On this research and development platform, we can probably push it about 2 kilometers out and still have really good communication and all the data being brought back through. We have this big robotic arm on the side of the robot that is used on one of our projects to grasp sample from the ground or from a drilling module and distribute it to the different instruments that we have. So it's being used with the scoop to go down, get that sample and deliver it to the different instruments.
NASA-ina daljinska tehnologija ne svodi se samo na kontrolu i upravljanje. Napredni autonomni uređaji uzimaju i analiziraju uzorke prije nego što ih donesu na Zemlju.
So I mentioned different data types, and I know that's kind of a nerdy term, but the different things we need to look at. So think about, what do we need to know? We want to know where we are. Where are we in space, or where are we on the surface? Okay? So to do that, we've got mapping components, and you can see we've got a bit of a traverse path on the moon mapped out there. Okay, so that's where are we in space. This is where we are in time, and that's a set of activities that says, here's what we're doing now, right? Here are these activities in time order. And then from there, those activities would be decomposed into procedures, which are step-by-step representations of how we do things, okay? And then to follow along and say, okay, here's where I am in space, here's where I am in time. Am I doing what I'm supposed to be doing? And for that, we look at telemetry, okay? Telemetry just means a remote measurement. Tele is remote, right? Telemetry, and then meter, okay? And to do that, we look at telemetry and we look at it in different ways. Right now, we're showing plots, right? Over time. Think of a measurement like a temperature or a voltage on a vehicle to see if it's healthy. We have these in our cars, okay? And then there's a representation of our rover, and you can see we've got references to telemetry in tables as data points linked to that rover. And then as a mission controller, I have to keep a log of what I'm doing. So here we have a notebook, And you know, that just looks like a notebook, but to me, this is amazing, okay? Because when I first started working with the space shuttle, you know, I was doing this by hand, all right? And I had to reference a telemetry point and say, okay, this measurement is this in this notebook, and I had to write my timestamps down by hand. This does it all for you, okay? I write something down, all I have to say is what happened, it's gonna capture the time for me, I can link my data to that, and that's that data integration because all my data is in one place. So if anybody has lights in your car, right? Status lights, maybe a check oil light, maybe your car's overheating light. Now cars don't really overheat anymore, but they used to. We also have status lights. You can see that banks of them here and banks of them here. And the last piece of the software that I'll show you is imagery. If you are driving, you want to know where you are. Now we have specialized software for rover drivers, which you'll see, which gives a view just for the drivers, but for all the other mission control disciplines, and the drivers use this as well, we have imagery. So when you go to each one of these waypoints, you can get a set of images, and it looks like a film strip because you can go back in time, you can go back through history and see where you were at any given time. If you go back and look at the old Mission Control Center, the Apollo Mission Control Center, you will see banks of lights. And when I started my career in Houston working on the space shuttle, that's what we still had. And we would, by hand, create what these displays were going to be. We had a plastic overlay that we put over these lights, linked to a little light that went on or off. That's all we could do, okay? Now we have complex logic that we can put behind these status lights. And once again, without writing a line of code, a mission controller can go in and create complex logic. So we're really excited about that capability.
Prateći napredak tehnologije, NASA razvija mnogo inteligentnije uređaje koji operiraju s određenim stupnjem autonomije.
So what we're looking at here is rover driving software. So this is specialist software that's developed for addressing some of the challenges of operating a rover on the moon. So the challenges of operating a rover on the moon are kind of akin to trying to operate like a remote control vehicle that you can't see, that has a camera attached to it taking still images. So you're effectively blind while you're driving, and then you stop, you take some images, figure out where you are, and then decide where to go next. So this tool takes information taken from the cameras on the rover, and it has two cameras on a steerable mast. It takes that information and it uses it to build up a 3D map of the terrain around the rover. So before we get to the moon, we're going to have information about the terrain, so that is the craters and the rocks and so on the moon, only down to a certain resolution. And below that, there can still be features that are large enough to damage the rover or cause the mission to be a failure. And we don't want that to happen. So what we will do is take images from the rover. They're stereo images, so we can extract 3D information from that. And then we use that to build a higher definition terrain map around the rover itself. And that software will also apply sort of a qualitative assessment of the safety of the terrain around the rover. So the colors that we're seeing here, green is terrain that is safe to drive on. Yellow is kind of not so safe, and then red are areas that you should probably avoid. How do you drive a rover on the moon? It's what we call waypoint driving. So essentially the first thing I'll do is look at the environment around me, and I see lots of green over here, so that means that this is fairly safe ground to drive on. So what I'm going to do is I'm going to drop a waypoint over here and then click Command Drive. And in terms of actually commanding the rover to drive, that's pretty much it. What that's going to do is build a sequence of lower level commands that will be sent up to the rover. But what we're seeing here is the simulation of the delay, the communications delay between here and the moon.
The farther away we are from Earth, the more autonomy becomes a requirement to be productive, okay? Whereas on the moon, autonomy is not a requirement for driving because we have a very short command cycle. So the types of autonomy we're talking about for this rover, because we want this to be a simple, low-cost robot, are things like virtual bumpers, right? Where the sensors would prevent it from doing anything to hurt itself, but not the type of capability where you can say, okay, I'm going to drive a long distance autonomously. And if you think about an autonomous car, it has roads, stop signs, a whole series of markers that are predictable and understandable. And we don't expect to find that on the moon. So it's more risky at this point to create a full autonomous capability for the moon. And that would be more expensive than we require at this point. We are in big trouble if we fall to the side. We wouldn't have any way of righting ourselves. So we have to do what's called waypoint driving. So waypoint is just what it sounds like, right? I'm going to specify a point, right? A rover driver is going to specify a point. They're going to go from here to there, all right? And then they're going to do another waypoint. And getting along this track is a series of waypoints. So it's an end-to-end capability of planning traverses, conducting simulations, and then viewing that mission control data.
The wheels are kind of moving by themselves here, and that's the rover kind of autonomy, making kind of fine adjustments and so on to keep the rover safe and headed in the right direction. So the simulator is simulating the lighting and some of the physical conditions, and that information is being fed back into this driving tool here. So we're using these tools together to train future rover drivers how to operate rovers on the moon.
Uspjeh ne dolazi lako. Često su upravo neuspjesi omogućili NASA da ostvari velike skokove u razvoju novih tehnologija.
During this time, the missile was stable in pitch, yaw, and roll. Then a failure occurred involving one engine. And shortly thereafter, another engine also lost power. It was therefore necessary for the range safety officer to destroy the missile by remote control.
Neuspjeh je koristan jer vam omogućuje da postanete pametniji i otporniji, a kad sljedeći put pokušate, imate mnogo više izgleda za uspjeh. Zbog spremnosti da riskira i suoči se s neuspjehom, NASA je danas predvodnik u inovaciji tehnologije.
Astrobi uses visual tracking to determine where it is. And you can see that on the walls of this area, we actually have photographs of the real International Space Station so that we have a realistic visual backdrop for testing the navigation algorithms. The size and shape of this area is about the same as the Japanese exploration module, or Kibo, of the International Space Station. When we're practicing docking with Astrobi, we can use this called the gantry flexible test rig. This gantry can push on the Astrobi robot with a lot of force. And if we had a completely fixed test rig, then we would be in danger of crushing Astrobi against it. But this actual unit here has a lot of flexibility to move around.
3D printing is a big part of the research and development process because it enables us to very quickly mount something on the robot itself. And eventually we usually switch to more robust manufacturing technique. But with 3D printing, in a day, we can mount the camera in a completely new location, for example. In this case, the ground camera, which is used to observe what's happening on the ground and in the scoop. And this is the work of a few weeks, basically. And hopefully we gain some very useful information of what the camera is seeing. And then this information is being validated by the scientists in order to get the best placement possible. So I'm going to show you how our rover works by driving it around and showing you how it deals with obstacles.
Kad vidimo svu tu uzbudljivu tehnologiju i cijeli svijet inovacija koji možemo otkriti u njezinim istraživačkim institutima diljem Sjedinjenih Država, sasvim je jasno zašto je NASA globalni predvodnik na području istraživanja svemira. Sada, nakon više desetljeća iskustva, kad imaju obilje resursa i istraživačkih projekata, niz inovacijskih centara, tisuće vrhunskih stručnjaka, neizmjerno mnogo prikupljenih podataka, kad su iza njih veliki neuspjesi koji služe kao prilika za učenje i silni uspjesi koji mijenjaju svijet te nas nadahnjuju i motiviraju, usavršili su proces i donijeli vrlo mudru odluku o suradnji s velikim i malim partnerima kako bi ostvarili snove čovječanstva. Za timove NASA-inih odjela za istraživanje i razvoj svaki je dan novi početak. Uz iskru nadahnuća i mnogo marljivog rada krenuli su nepoznato, beskonačnim putem ispitivanja i otkrivanja. S toliko inovacija koje treba izumiti i svjetova koje treba osvojiti, mogućnosti su doista neograničene.